All right, so this lesson is going to be on the end behavior of a polynomial function. And then at the end, I'm throwing in some other types of functions just to give you kind of a sneak peek on what's coming up. But most of this lesson is on polynomial. And so the end behavior of a function describes how the function behaves as it moves infinitely to the right and to the left. In other words, the end behavior is what happens to the values of f of x as x increases or decreases without bound. So what you're going to learn a brand new notation, that's limit notation. And if you take calculus next year, we'll talk about limits like for the whole month of August. And so this today actually is we're still using limits today. So this is a huge part of calculus, but this year we're just going to use the notation to describe what's going on the graph. And so this is limit notation. And the way you would read this is you would say the limit of f of x as x approaches negative infinity. And that represents the left side of the graph because that's where x is approaching negative infinity, to the left, far left. All right, and then what it means is as the values of x decrease without bound, which means going towards negative infinity, the y values of fx, they do something. And so for polynomial functions, they're either going to increase without bound or they're going to decrease without bound. All right, so let's look at example 1. On example 1, we're going to describe the end behavior verbally, and we're going to use limit notation. All right, and so the left side is the same thing I just read in words. As the x values decrease without bounds, that's the left side always. And you probably want to write kind of small. There's not a ton of space here. And then I'm just going to continue writing what is typed up there. So the y values of f of x okay, so if we think about the x values getting smaller and smaller and smaller, farther and farther and farther to the left, what are the y values doing? They're increasing. They're getting larger and larger and larger. So we would say the y values of f of x increase without bound. And then we're going to write that with limit notation. So limit notation is a lot less writing. And so typically when I do a limit, I write it in cursive, kind of, like partially in cursive, partially not. You don't have to write it in cursive. That's just the way I was taught. So we're going to do the limit of f of x. And the left side is when x is decreasing without bound or when x is approaching negative infinity. So that's just, this is the same thing as writing what was in front of the comma. So how do you think we're going to represent the y values increasing without bounds? What number would that be? Kind of a number. So they just get bigger and bigger and bigger. What are they approaching? Infinity. Right? So that's just a fancy way of saying that on the left side, the arrow is pointing up. Right, and then we have all that same stuff for the right side of the graph. So the right end behavior is when the limit of f of x is approaching infinity. Sorry, the limit of f of x as x approaches infinity. So approaching infinity is the right side. and then we'll describe what the y values are doing over there. So the right side, the x values increase without bound. All right, and then when we look at the graph, what would you say as the x values are increasing, what are the y values doing? Decreasing without bound. Good job. And then we'll describe that with limit notation. The limit of f of x. The right side is going to be as x approaches positive infinity. All right, what are the y values approaching negative infinity? Good job. Okay, I'm going to have you guys do B on your own. As I'm walking around, if you have a question, please let me know. Both sides of the end behavior are increasing without bound or approaching infinity. All right, so what questions do you guys have? Okay, so on the next example, we're just going to do a couple of sketches. And so we're going to sketch a polynomial that has the following end behaviors. Now, one thing about polynomials, and we'll talk a little bit more about this tomorrow, is they're continuous. And so you can draw the whole polynomial without picking up your pencil, and they have smooth, rounded turns. So as you draw these polynomials, make sure you don't make any like sharp turns, but other than that, you should be good. So on A, we want a polynomial that on the left side is pointing down and on the right side is pointing down. It could just be a parabola if you wanted it to be, or you could add some changes in direction. It doesn't matter as long as you have smooth rounded turns. The arrow on the left is pointing down and the arrow on the right is pointing down. Right, same thing on B. It could be a line if you wanted it to be, but on the left side we need to be pointing down, on the right side we need to be pointing up. In between, it doesn't matter as long as it's smooth and rounded and connected. Now another thing you're going to need to be able to do is look at the algebraic form of the function and tell the end behavior without a calculator. And this is something that you did in Algebra 2. You wrote it differently, but it was still the same thought process. And so for me, and I might teach this differently than your Algebra 2 teachers, I don't know. But for me, I always figure out the end behavior on the right side first. I think that's the easiest way to remember this. If the right side is going to go to positive infinity if the leading coefficient is positive. Now it's been a few days since we talked about leading coefficients. It hasn't been that many topics, but we've spent so many days on topic 1.5. But the leading coefficient is going to be the number in front of the term with the largest exponent. So if that number is a positive number, the right side is going to go to positive infinity. The right side is going to go to negative infinity if that leading coefficient is negative. Right. And then the left side depends on the degree. And so the left side goes in the same direction as the right side if the degree, do you guys know, even or odd? Even, good. And then opposite of the right if the degree is odd. So if we could look back up at what we drew for A, would you say that's even or odd degree? It's even. Would you say the leading coefficient is positive or negative? Negative. The right side is pointing down. The leading coefficient is positive. All right, is B even or odd degree? Odd degree. And what about the leading coefficient? Positive. Good. Okay, so now let's look at these. So sometimes the leading coefficient and the degree are super obvious, like on the first one and the second one, there's only one term. So the leading coefficient is definitely 4, and 4 is positive. So even though I've been doing this for like, I don't know, 25 years, I still do the right side first. So if the leading coefficient is positive, the right side is positive infinity. And then to figure out the left, my degree is an odd degree. And so the left is going to be opposite of the right. Right, then when we look at B, there's only one term. So it's obvious that the leading coefficient is positive 1/2. So the right side is going to go to positive infinity. The degree is 4, which is even. I was about to spell even wrong. All right, so that means that the left side is going to be the same as the right. Okay, the rest of them, the leading coefficient isn't as obvious. All right, so for number 6, what do you think the degree is going to be if we multiplied all of this out? X to what power? The 6. So the term with the largest exponent is going to be x to the 6th. What do you think that leading coefficient is going to be? -2. Good. So that would be, if I multiplied it all out, that would be the term I would use to get my leading coefficient and my degree. And so that's definitely a negative leading coefficient and an even degree. right, for for letter D, what term do I care about? Just this one. So the leading coefficient is definitely negative. The degree is odd, so we'll do opposites. All right, on E, what term do I care about? Still this one. And so it's going to be the same. So it doesn't matter what's added or subtracted to that. When we're doing the end behavior, all that matters is that term with the largest exponent. All right, and then on F. So whenever you're trying to figure out the degree, what I would do is I would multiply 2x times negative x. What am I going to get? 2x times negative x. Negative 2x cubed. That's going to be the term you would use to make all your decisions. So that one ends up being like C through F. All right, any questions? So it's very much like what you learned last year, just maybe kicked up a notch with new notation and maybe a little bit more difficult to find the leading coefficient. All right, and then example 4, we just have some plain old polynomials written in standard form. We're going to do the limit statements for the end behavior. So I'm still going to start on the right side. So on the right side, because that's a negative 3, I am going to go to negative infinity. And then the left side, because it's an even degree, I'm also going to go to negative infinity. All right, so B is the first one where we're writing limit statements. I think that's not F. So I didn't grade the question on the AP exam that used limit notation. There was one. So I don't know if they took off points for you calling it the wrong thing, but let's call it the right thing. So B is G. All right, so you guys do that one on your own, please. So, do you guys have questions? Okay, let's look at the last ones. The last ones tell us to use a graphing calculator. If you don't have one, it's fine. If you have one, get one out. I'm actually not going to use a graphing calculator on the first one, because I really want you guys to know how to do this without a calculator. So what is the shape of A going to be? Parabola. Is it going to be upward or downward? Upward parabola. So I feel like that's something you guys have known like since algebra 1. So don't use a calculator to graph a parabola. Just do it in your head. You got this. All right, then we can do the new stuff, which is the limit notation. All right, both those arrows are pointing upwards, so both of those are going to positive infinity. All right, so I said that we have a sneak peek at some new kinds of functions. So is b a polynomial function? There were certain rules about polynomial functions. So the exponents had to be positive integers, and like we can't have anything like where we're dividing, because that is kind of like a negative integer. So b is definitely not a polynomial function. And I don't think you've ever graphed one of these functions. They're called rational functions. So let me show you what the graph looks like. This is what the graph looks like. So as x decreases without bound, does the y increase or decrease without bound? Doesn't. It goes flat. So where you're looking, you can't really tell, I don't think, maybe you can, where it goes flat. We'll learn how to do it soon, actually. But let's look at the table. So this is still scrolled. So I'm going to decrease without bound. I'm going to go small. Well, I'll have to stop at some point because this is the calculator. What do you think the y values are getting closer and closer and closer to? 2. So that's going to be my left limit. Oh, let's go ahead and get a little graph there. All right, so what I want you guys to do is draw your little axes. And the only little number we care about is y, 2 on the y-axis. Everything else we'll just kind of guess. So 2 on the y-axis, draw a little dashed line for me. And we'll, like I said, this is just a sneak peek. We're going to learn all kinds of stuff about these graphs. And so it's going to be flat against that line and then curve up. And then kind of do the same thing over here. So we looked, and on G, as x decreased and decreased and decreased and decreased, the y got closer and closer and closer to 2. So that is the value of that limit. All right, and we could do the same thing in the other direction. So some weird things go on at the middle, but then as we just get bigger and bigger and bigger on the x, you can tell that y is getting closer and closer and closer to 2. Now eventually your calculator will go to 2 just because of rounding, but in actuality it doesn't get to 2, it just gets slightly closer and slightly closer and slightly closer. It approaches it. Okay, and this is another graph that I don't think you would know what it looks like. So negative 10 over x squared. Okay, that's what that graph looks like. Right. As x decreases without bound, what does it look like the graph is getting closer to 0? And then increase, same thing. That's a symmetric graph. I guess that technically looks like it would be, well, yeah, that's an even function because it's a reflection over the y-axis. I didn't draw it perfectly, but it's okay. All right, so those two, like I said, they are just sneak peeks into other types of functions that we'll talk about, but your assignment is all about polynomials.